So in the field of psychology, multiple regression is much more used than bivariate regression. For instance, let's say that you wanted to predict an outcome or dependent variable. It's not very realistic to look at only one predictor variable, because any psychological outcome, there's going to be a number of important predictors. For example, let's say you wanted to predict depression. So depression was our dependent variable or criterion variable. Then you may have predictors such as self-esteem, relationship satisfaction, perceived social support, financial security, work satisfaction, or even the level of physical activity, and so forth. So that may all be related to the incidence of depression. So the B attached to variables tells us, the coefficient B tells us something about the relationship between that particular predictor and the thing that you're trying to predict. Now, to explain what multiple regression does, I want to reflect on what bivariate regression does and then step it up to a multiple regression where there are two predictors. So if I take your mind back to bivariate regression and an example, and let's use the same example that I've just sort of shared with you earlier, number of dates. So let's say the number of dates is equal to A, which is our constant, plus B1 attractiveness. So I collect a bunch of data that records the number of dates the participant has had over the last three years and a score of their level of attractiveness. These data points are the dots that you can see that is positively correlated. Then through a process of something called ordinary least squares, a line of best fit is drawn. Now, I talked about ordinary least squares in the previous lecture on bivariate regression. Now this line of best fit, that allows the best possible prediction of the y-scores, so of the predicted y, the y-hat, from the knowledge of the x-scores. In other words, it's the best possible prediction of the number of dates from your score of attractiveness. Now the difference between the actual number of dates, which is y, and the predicted number of dates, which is y-hat, is the error in prediction. Errors in prediction are known as residuals and are the difference between the actual y-scores and the predicted y-scores, so y minus y-hat. This least squares regression line aims to minimize the sum of squared residuals. Now, when there are two predictors, such as in multiple regression, and we see number of dates is equal to A plus B1 attractiveness plus B2 personality, all of a sudden you have three axes that capture the three variables. Your data would fall on a graph that looks like this. Now I've plotted this data on the graph. You can see a number of dates are on the y-axis, and the other two axes are attractiveness and personality. So what we're looking at here is a three-dimensional graph. Now if you take your mind back to bivariate regression, a line of best fit was done that best fits all the data points. This was a two-dimensional line of best fit, and the data was drawn up through a process called ordinary least squares. Well, now because we have three variables, one of them is the criterion and the other two are predictors, we have a three-dimensional graph, and the best fit of this data is now not a regression line but a regression plane. So through a process that's similar to the bivariate regression model, I find a regression plane that best fits that three-dimensional set of data points to the number of dates from attractiveness and personality, and use that to plot what's known as a regression plane. So if you take all these points and you try to find the line or the plane that best fits them all at once, you get that plane of best fit. What this means is that the line on the scatter plot, or the plane on the scatter plot, is closest on average to all the observation points that you can see. Now geometrically, the sample regression plane is a plane that minimizes the sum squared vertical differences between the observed values of y and the values of y predicted by the regression plane. The computation of the estimated regression coefficients is rather complex, and the formulas and their values are cumbersome without using matrix notation. So I'm not going to go into this in this lecture, and it's beyond the scope of this course. But usually for real life applications, we're not able to determine exactly the value of the variable we're trying to predict, even when we know the values of the predictor variables. For example, in the case of number of dates, there are many factors that affect the number of dates a person may have that are not accounted for by attractiveness or personality. So we're going to have errors in prediction. And errors in prediction are known as residuals, and the difference between the actual y-scores and the predicted y-scores is y minus y hat. They're your residuals. This least squares regression plane aims to minimize those sum of squared residuals. So when we're looking at the equation, number of dates is equal to A plus B1 personality plus, B1 attractiveness plus B2 personality, the model is linear because it's linear in the parameters of A, B1 and B2. The model describes a plane in the three-dimensional space of the number of dates, attractiveness and personality. The parameter A is the intercept of this plane. Parameters B1 and B2 are referred to as partial regression coefficients. Parameter B1 represents the change in the mean response corresponding to a unit change in attractiveness when personality is held constant. Parameter B2 represents the change in the mean response corresponding to a unit change in personality when attractiveness is held constant. I'll talk more about this soon.